Hello, Amma. Good evening. Let's start the class for the second day. Right. So today we are going to discuss about the cathode rays. Right. Before that, let's go through the things what we have learned last day. Quick recap. Right. What we have learned last day, Amma. One of the last day. 𝐓𝐞𝐥𝐶𝐫𝐚𝐦. Right. The very last day. Right. Last day we had started with the origin of atom. Right. So the atomos, that word is actually introduced by who? Democritus and Greek philosophers, right? Those are the ones which introduced the atom to the world. But then we had discussed about the 4 postulates of Dalton, which gave a precise picture of the atom. Right? What were the 4 postulates and their failures? Dalton said that the indivisible, uncuttable, the tiniest and the fundamental particle of matter is atom. He reintroduced the word atom to the world, right? In 1808. Then what was the failure? Why we are not considering that thing as true nowadays, right? So we know that atoms are made out of electrons, protons and neutrons. අපි දන්නවා නේද atoms තියෙන්නේ electrons, protons, neutrons එක. Right? So that means atoms can be divided. Atoms can be divided into neutrons, protons and electrons. Right? So that uncuttable, indivisible part no longer appear with the atoms. Right? So as we know now, the subatomic particles exist, right? So we are not following that first idea, the first postulate of Dalton. Right. Second thing, he said that atoms of same kind, atoms of same element are identical with mass and size. Atoms of same element are identical with mass and size, but atoms of different elements are different. That thing is also not accepted today, as we know the existence of isotopes. Right? Isotopes are the species, or isotopes are the atoms of same element but with different masses as their number of neutrons change. Right? Third postulate of Dalton. Dalton third one. He said that atoms can't be created nor destroyed in chemical reactions. Right? So atoms create කරන්නත් බෑ, destroyed කරන්නත් බෑ කියලා තමයි තුන්වෙනි Dalton කියන්නේ. His third postulate. But nowadays we know that atoms can be created as well as destroyed. Actually, those will be done by nuclear reactions. We had discussed about the carbon-14 dating as well. Right there, the carbon-14 atom is destroyed to form or to create the nitrogen-14 by releasing a beta particle. So by nuclear reactions, this creation as well as the destroy of atoms occur. Right? So that we are not following the Dalton's third postulate as well. For chemical reactions, that is true. That is what mass conservation means, but that is not valid with the nuclear reactions. Right. Next one, the fourth postulate. The fourth postulate was all about forming compounds. He said, when atoms join together or combine together to form compounds, they will combine with simple numerical ratios, simple integer or numerical ratios. That was the fourth idea of Dalton. But nowadays, that is also not accepted, as with most of the some of the compounds are available, right? Without the simple ratios. We had came up with the carbon 17H37, C17H36, sorry, C17H36, that hydrogen. So even we came up with the C12H22O11, right? So that molecules. With those, we know this ratios are not that much simple, right? And some solid state material also can be found with fractional values as well, rare but existing. So with that, Dalton's fourth postulate is also not accepted today, right? Those are the things we had discussed with Dalton's four postulates last day. Then we had discussed about the electric nature of matter and the evidences, right? So three evidences to discuss where the matter is interacting with charge as evidences for that. So we had discussed about static electricity, and we had discussed about the electrolytic cell processes, the electrolysis process, as well as we had discussed about the electrochemical cell constructed with zinc and copper electrodes. We had discussed the process there, right? And then we had ended our discussion with the Stoney's statement. What was the Stoney statement? The Stoney said, if when considering material or matter, if you have a fundamental, that means uncuttable, indivisible, right, tiniest unit for matter, if there is kind of something like that as atom, so there should be something like that. That means some kind of thing like uncuttable, indivisible, tiniest fundamental unit for charge as well. That was the Stoney statement, and he named the charge, the tiniest fundamental charge, as electron. So the first idea of the electron is actually done by Stoney. So that was the place we had ended our discussion last week. Right? Today we are to discuss from there onwards. Right? Stone 𝐓𝐴, right? There should be a tiniest fundamental unit for charge as well, uncuttable, indivisible unit, right? Then scientists began to find that thing. That means they start the search to find that tiniest, right? The uncuttable, the fundamental charge unit, the electron, right? So first evidence. So for the first succeeded experiment is actually done by the William Crookes. In right, මේ particle එක හොයාගන්න වැඩ කරන් යද්දි ඒගොල්ලෝ succeed වෙච්ච first experiment එකන්නේ William Crookes කරපු experiment එකකින්, right? So William Crookes invented some glass tube, right, called as cathode ray tube, or those days it is referred to as the Crookes tube, right? So let's discuss about his experiment which led to, right, the first occurrence of, right, first observation of cathode rays, right, the electron, right? So William Crookes came up with this kind of apparatus. Right? He came up with this kind of apparatus, right? Some glass tube and two terminals were there, two metal plates were there, which are connected to a considered high voltage, right? We can think of kind of 5,000 volts connected to a high voltage. Let's say this is the negative terminal and this is the positive terminal. So these plates can be referred to as the cathode and the anode. And when it comes to this glass tube, right, he came up with almost a vacuum. That means gas molecules in the tube is almost completely removed. Right, gas molecules right, created almost a vacuum. That means he came up with a very low pressure inside the tube, right? Very low pressure. Well, pressure means actually it is kind of a measure of gas molecules in the tube, right? Pressure කියන්නේ right tube එකේ තියෙන gas molecules කියන measure එක. ඒ ගැන පොඩ්ඩක් කතා කරලිමුද අපි මේ experiment එකේ observation එකට යන්න කලින්. මොකද William Crookes maintain කරේ very low pressure inside the tube. Right, that means very few amount of right gas molecules he had maintained inside the tube to see this observation, right? So it's like this now, right? Pressure means force over area, right? Pressure means the force applied on unit area of this glass vessel, right? Unit area එකට applying force එක තමයි pressure කියලා අපි කියන්නේ, right? If you are with greater number of gas particles, inside the tube like this, right? So more collisions will occur with the walls of the tube by these gas particles if you are with greater number of gas particles there inside the tube. So more collisions will occur with the walls of the gas tube means more force will be inserted. So force will be high. When the force will be high, so your pressure will be high. See, when more gas particles are there, more will be pressure. When less gas particles are there, right? Less gas particles are there. Very few collisions with the walls of the glass vessel. So few collisions means few force. The less force will be applied to the walls of the container. That means pressure is low. Alright. So pressure is a measure of gas molecules inside the tube. Alright. So he had maintained a very low pressure inside the tube. That means very low number of gas molecules inside the tube. Then he has observed some kind of glowing. He observed some kind of glowing started from the cathode and going towards the anode, right? Yeah, right? Some glowing is originating from the cathode is actually started to move towards the anode. William Crookes observed as these rays are produced from the cathode, he named these rays as cathode rays, right? Cathode being originated is එයා මේකට cathode rays කියලා කිව්වා. That is the first observation of cathode rays. Again, I'm telling what he has done. මොකක්ද එයා කරේ? He has came up with a glass tube with very low pressure. It's a near vacuum. Almost all the gas molecules have been removed and came up with a very low pressure inside the tube. And he had some two metal plates inside the tube, and which were actually connected to a very high voltage. Connected to a very high voltage, right? So very low pressure and high voltage is maintained. When these conditions are applied, he had seen some glowing, which is actually started from the cathode, and it is moving towards the anode. It's seen some glowing appearing. It started from the cathode and moves towards the anode. That was the first observation. As those rays are started from the cathode, he had named these rays as cathode rays. Cathode rays. The idea is clear? That is the first observation of cathode rays. And then the important thing to know here is actually cathode rays are colorless. Cathode rays are colorless. Or දැනගන්න ඕන වැදගත්ම කාරණා තමයි cathode rays colorless. පාටක් නැහැ එහෙම. Then how the Crookes and the crew was able to see these stuff? The cathode rays colorless. ඉතින් colorless නම් කොහොමද මෙයා මේක දැක්කේ? If the cathode rays are colorless, now we have a problem. How those guys were able to detect the presence of the cathode rays? Cathode rays තිබ්බා නැත්නම් මේක දැක්කේ කොහොමද? Colorless. Right? So let's examine that. We'll discuss how they were able to see these rays, detect these rays if they are colorless. That problem is there. And we'll discuss why it is very important to maintain a low pressure here inside the tube, and we'll discuss why we need a high voltage as well. Right? So I think cathode ray tube එක කතාව පැහැදිලිනේ. So මෙතෙන්ද mainly කතා කරන main කාරණා තුනක් තියෙනවා. එකක් තමයි අපි කතා කරමු ඇයි very low pressure එකක් maintain කරන්න ඕනේ. සහ ඇයි high voltage එකකට අපි යන්න ඕනේ to see the observe the cathode rays. Right? And why and then how these guys were able to detect the cathode rays if those are colorless. Or colorless නම් ඇයි මෙහෙම දෙයක් කොහොමද මෙහෙම දෙයක් දැක්කේ? Right? හරි. අපි එහෙනම් කතා කරමු එකින් එක. Right. The first thing we'll discuss how these guys were able to see these rays. කොහොමද මේගොල්ලෝ මේ rays දැක්කේ කියලා? If they are colorless. The thing is like this now. Right? Even though these cathode rays are colorless, those were able to, right, emit light from some scintillating material, from atoms of scintillating material. Let's discuss what it means. Let's think this kind of atom of some scintillating material, right? Okay. So these material or these things are there inside the gas, as well as they have painted the walls of the cathode with these scintillating materials. The scintillating materials are some material which will emit light, right? Gain some energy. When they are able to gain some energy, or when the cathode rays are hit, right? So these materials will emit light. So we'll discuss how these things happen. right? So atoms of scintillating materials, normally these things are there as gas molecules, right, in gas molecules as well as in glass, right? So what will happen, right? So atoms are like this, that 288, you know the stuff, no? So electrons will be like this, right? And when the cathode rays come and hit the electrons of these materials, so these are cathode rays, which are colorless. In these guys comes and hit these electrons of the cathode rays. What will happen, right? These will jump. This will jump to the higher energy levels by absorbing this energy given by the cathode rays, right? Cathode rays are with some kinetic energies, no? Those are moving, no? Kinetic energy is there. So it can transfer that kinetic energy to electrons in your scintillating material. As electrons are absorbing that energy, it will move to higher energy levels. Now, සාමාන්‍යයෙන් atoms වල energy levels කියන concept එක පොඩ්ඩක් තේරුම් ගන්න. එතන වෙන්නේ හිතන්නකෝ ඔයාගේ electron එකට තියෙන්නේ 10 joules of energy කියලා. ඔයාගේ electron 10 joules of energy එකක් තියෙන්නේ. යා ඉන්නේ මෙන්න මේ energy level එකේ 10 joules. If the atom the electron is with 20 joules of 25 joules of energy, it will stay at a higher energy level, right? Nucleus එකෙන් ඈතට යන energy level එක energy එක වැඩි වෙනවා. දැන් yield energy එක කියලා කියන්නේ ඔයාගේ තියෙන්නේ 10 joules of energy නම් එයා ඉන්නේ 10 joules වලට දාලා energy level එක. ඔයාගේ electron එක තියෙන්නේ 25 joules නම් ඒ electron එක ඉන්න ඕනේ 25 joules වලට දාලා energy level එකේ. That is the idea. So for an electron with 10 joules, if the energy of the cathode rays is also transferred, let's say these cathode rays are carrying some 15 joules of energy, so that this will absorb that 15 unit and it's right, and then move to the 25 joules energy level, right? So that will happen. So electrons will jump to higher energy levels, and with time they will come back to the original state by actually releasing the excess energy they were with at the higher energy level. ඉතින් higher energy level තිබ්බ excess energy එක අතර 15 joules කියන එක release කරලා ආයතරයක් 15 energy level එකට එනවා. අන්න ඔහොමෙද්දි මේ release කරන radiation එක electromagnetic spectrum එකේ visible region එකේ තිබ්බොත් මේ radiation එක electromagnetic spectrum එකේ visible region එකේ තිබ්බොත් ඔයාට color එකක් observe වෙනවා. ඔය විදිහට තමයි cathode rays were able to, right, produce light, produce colorful glowings from scintillating materials, right? The cathode rays are colorless, but scintillating materials will emit light when hit by the cathode rays, right? So with this we are able to detect the pathway of the cathode rays. දැන් අර මේක එක තැන්වල ඔයගේ scintillating materials තියෙනවා. ඒ කියන්නේ gas එකේ scintillating gas molecules තියෙනවා. So that when the cathode rays go through the gas, when they hit the respective gas molecules, the scintillating gas molecules, right, they will emit lights. So with that they can detect the pathway of the cathode rays. Cathode rays යනකොට එතනින් එයා bulb එක පත්තු වෙනවා, right? යන path එකේ පත්තු වෙනවා, right? So then we can detect the direction of travel of cathode rays. That is how they were able to see the cathode rays. Not because cathode rays are colored, but because the cathode rays are able to emit light from the scintillating materials which were there at the gas as well as in the walls of the tube. right නේද? කොහොම තමයි cathode rays observe කරන්නේ. පැහැදිලි? right. ඊට පස්සේ අපි බලමු කතා කරමු ඇයි මේ very low pressure එකක් maintain කරන්න ඕනේ මේ gas tube එක ඇතුලේ. Why we need to maintain a very low pressure here? ඇයි මේ very low pressure එකක් අපිට ඕන කරන්නේ gas tube එක ඇතුලේ to observe the cathode rays. Cathode rays observe කරන්න. හරිද? ඇයි එහෙම ඕන වෙන්නේ? The thing is this line. So if we had some greater amount of gas molecules like this, if you had very greater number of gas molecules inside tube like this, then the tube එකේ මේ වගේ ලොකු gas molecules ගන්නක් තියෙනවා. That means your pressure is high, right? If you have this amount of higher number of gas molecules, that is what meant by higher pressure, right? So මොකද වෙන්නේ? උත්තර ළමයි, right? මෙතනින් produce වෙන cathode rays වලට අතන වැඩි දුරක් යන්න වෙන්නේ නැහැ. Cathode rays are unable to travel far. Why? All the energy of the cathode rays will be absorbed by the molecules in this section. So it is unable to travel towards the anode then. As the concentration of molecules are high, with higher pressure means, right? Higher pressure means higher number of molecules in unit volume. No? So high number of molecules are there. No? So as concentration of molecules are high, even near the cathode, right? All the energy of the cathode rays, the kinetic energy of cathode rays will be absorbed by these nearby gas molecules, and cathode rays are unable to travel longer towards the anode. So you won't see that glowing, right? Going towards that green colored glowing going towards the anode can't be seen then if more gas molecules are there, right? But if kind of a very low pressure is maintained, low pressure එකක් maintain කරන මොකද වෙන්නේ? අර ඒ වගේ gas molecules එච්චර ප්‍රමාණයක් නැහැ nearby the cathode, you won't have such amount of large gas molecules. So cathode rays will go, right, some distance, able to go some distance. So as very limited amount of gas molecules are available. See? So cathode rays can travel towards the positive plate, right? So we can see the green color glowing, right? Going to starting from a cathode, going towards the anode. That is possible only when very limited amount of gas molecules are there inside the vessel, inside the glass tube. So that pressure should be maintained at a very low value. Very limited amount of gas molecules means very low pressure. So pressure is a measure of gas molecules, right? නේද? කොහොම තමයි ඒ කතාව සෙට් වෙන්නේ. හරි නේද? That is why we need a very low pressure there. The things are clear, right? අපි මේ ටික ලියා ගමු ළමයි. Right? Let's write this stuff in your note, and let's go to the note first of all, and then we can write the stuff, right? In your note, it is said during the mid 1800s, right? During the mid 1800s, scientists began to study electrical discharge through a glass tube pumped almost empty of air, right? This device was an invention of British chemist and physicist William Crookes, and is called Crookes tubes or Crookes ray tubes. Sorry, cathode ray tube. Sorry, right? You don't know. Are things are written, no? Okay. So when two electrodes are connected to a high voltage source, the heated negatively charged plate called the cathode produced a stream of invisible radiation. This radiation emitted from the cathode was given the name cathode rays. Radiation emitted from the cathode given the name cathode rays. Fairly hard. So some spacing is there, some empty space is there to be written, right? So let's write this idea, right? අතන cathode rays color එක ගන්න. The color is observed as it had caused to emit light from the scintillating material, right? So we'll write that, right? Clear කමු දෙක කතාව. So you can write although let's write this. Although come to the red color and write. The cathode rays could not be seen. The cathode rays could not be seen. The cathode rays could not be seen. Come to the normal color. Their presence was detected. Their presence was detected. Their presence was detected because their presence was detected because cathode rays cause come to red color again and write. Gases at low pressure to glow. Gases at low pressure to glow. Come to the normal color and write. And again in red color. Which made other substance to fluorescence. Which made other substance to fluorescence. Which made other substance to fluorescence. Right now? Okay, Lama, you can draw this picture. This picture now me part this section. Cathode rays are colorless, right? But they can cause the fluorescence, the scintillating materials to give off light. Cathode rays මේ විදිහට scintillating materials වල තියෙන electrons වලට එයාගේ kinetic energy transfer කරාම ඒ electrons ඒ energy එක absorb කරලා higher energy levels වලට යනවා. When the electrons come back to the original state, they will emit the absorbed radiation as electromagnetic wave. When those electromagnetic waves comes under the visible region of the electromagnetic spectrum, you will see a color. සාමාන්‍ය කොළ පාට වගේ තමයි දැක්කේ ඉතින්. proofs use කරපු tube එකත් එක්ක ඒ scintillating materials එක කොළ පාට වගේ තමයි green color going තමයි දැක්කේ. But remember, the cathode rays are not with green color. Those are colorless, right? So complete this stuff. So a friend is asking why we need to apply some high voltage here. A local voltage එක apply කරන්න ඕන කියලා අහලා තියෙනවා කරුවෙක්. Right, so greater voltage is needed to eject electrons from the cathode. Right, we need to supply some greater voltage. to remove these electrons from the cathode to the empty air. කවුරුත් මෙතන කිසිම particle එක material නැතුව නේද empty air එකකට almost empty. So very low pressure now. So here's some space almost empty, right? To that thing, to eject electrons, release electrons, right? You need to supply some great energy. That electrical energy is supplied via high voltage. නිකම් electrons release වෙන්නේ නැහැ නේද? හරිද? එතකොට ලොකු එනර්ජියක් ඕනේ වා. මේ පැත්තෙන් electrons pump කරද්දි ලොකුවට high voltage එකේ electrons pump කරද්දි negative terminal එකේ right මේ පැත්තෙන් electrons release වෙනවා ඩංගන. So greater electrical energy is applied needed to eject electrons from the cathode. That is the simple idea there. Become electrons release in NAND, right? So you need to supply some energy to eject electrons from the cathodic metal. Because you need to release those electrons to kind of a vacuum, almost vacuum, empty space. Empty space is release the anything itself. Or take body energy space can. It's not like the static electricity, right? Static electricity වගේ මේ හරි රබ් කරලා ගන්න පුළුවන් තත්ත්වයක් නෙමෙයි දැන් තියෙන්නේ. හරි. මොකද ඔයා empty air එකට තමයි empty space එකට තමයි electrons release කරන්න try කරන්නේ. So we need to apply some greater force there. Right? That is the idea. Okay. Shape. After that, let's discuss about the properties of the cathode rays. Let's move towards our discussion about the properties of the cathode rays. Cathode rays properties can right? So in your research book, right, they have discussed about 3 properties of cathode rays. First, let's go through those 3 properties actually which are discussing at the research book. Then we can discuss about few more as well, as those were asked in the past A-level paper questions. Right, first of all, let's start with discussion with the 3 major properties of cathode rays which were discussed at your research book. Right? Okay. Following property. The first property. Right? So cathode rays are actually travel in straight lines. Cathode rays actually travel in straight lines. Right? So how they had concluded that idea, confirmed that idea. Then me cathode rays lagi me properties में दारान lamai, they have came up with few changes to the original cathode ray tube. Actually, Thomson is a scientist who had done these experiments to come up with the properties of the cathode rays. Cathode rays properties so agan experiments kar J.J. Thomson came scientist, right? So he had done some changes to the original cathode ray tube to confirm or to come up with these properties, right? To come up with some experimental setups to confirm these properties, right? So the first property we are going to discuss here is actually cathode rays travel in straight lines. Cathode rays travel in straight lines. බලමු කොහොමද ඒක අප්‍රූව් කරන්නේ, right? J.J. Thomson came up with this kind of a cathode ray tube. Some changes had been done to the original cathode ray tube, right? So let's say this is the cathode, which is connected to the degree terminal of the high voltage source. And instead of the anode here, he connected kind of a opaque object, right? He came up with a metal cross kind of opaque object, right? Opaque metal object, right? As the anode. As the anode. This is the anode. Right? Then what was the observation? Yeah, what was the observation here? He had seen some shadow is appearing at the end, which is opposite to the cathode. Cathode එකට opposite end එකේ he had seen the shadow of this metal cross, the opaque object. හරිද? එතකොට ඒ opaque object එකේ metal cross එකේ shadow එක යා දැක්කා at the end opposite to the cathode. Right? So that is the observation. Right? Shadow of the opaque object of the metal cross. So as the anode, they come up with the metal cross, right? Right? This was the idea. This was the experiment setup. Here it came up with. And actually this observation proves that cathode rays travel in straight lines. The cathode rays travel in straight lines. How come? So if they can go with some curvy pathways you won't see the appearance of this shadow there. මේ curves විදිහට මෙහෙම යනවනම් අර කවදාවත් shadow එකක් දකින්න හම්බ වෙන්නේ නැහැ. As they are going as straight lines, traveling straight lines, as they can't go through this opaque object, these rays won't escape this opaque object. That is why some kind of dark shadow appearing here, as these rays are not being hit to this wall at these areas. Alright, that is how the shadow is formed. මේ rays ඔයාගේ මේ wall එකේ මේ තැන් වල වදින්න නැති නිසා තමයි you would see the shadow appearing. මේ හරියට rays ඇවිල්ලා වදිනවා, right? It is possible only if the cathode rays are only traveling in straight lines. Curves විදිහට නම් මේ වගේ shadow එකක් එන්නේ නැහැ. පැහැදිලි නේද? So that is the idea. And this is the experiment setup, and it changes down to the cathode ray tube to observe this observation. Right now, so quickly draw this one. So you have the cathode rays here, right? You have to label stuff, right? Cathode is there, cathode rays are there, anode is there. The shadow of the metal cross. Complete stuff. හරිද? Let's try this thing, this explanation. This clear? Sorry. Expression लिया गया है. When n come to the red color and write. Opaque object. An opaque object, come to the normal color, like a, come to the red color again, metal cross, like a metal cross, come to the normal color again, is placed in the path of cathode rays, in a discharge tube, put a comma and come to red color, and write a shadow with sharp edges, of metal cross, come to the normal color, and write is formed at the end, come to the normal color and write opposite to the cathode, at the end, opposite to the cathode. At the next line is just right. That was observation. Now we are writing the conclusion there. And the next line, just right. In normal color, right? The placement of the shadow proves that put a comma, and at the next line just write it in red color. I can continue at the next line put a dash and write cathode rays emit from the cathode. If the cathode rays are not emitting from the cathode, right, you won't see the shadow here, right, at the end opposite to the cathode. Cathode rays නිකන් නේද? හරි. cathode එකෙන් emit වෙන නැත්නම් මේ පැත්තෙන් එන නිසා තමයි ඔයාලට shadow එක මෙතන හම්බ වෙන්නේ. cathode rays මේ හරීම කියනවන්නේ. cathode මෙහින් එනවා shadow එක හම්බ වෙන්නේ මෙහින්. Right? You get the shadow at the end opposite to the cathode because cathode rays are emitting from the cathode, right? හරි. මෙහින් වගේ නිකන් emit වෙනවා හරියන්නේ නැහැ. මෙහින් එනවා නම් වාගේ shadow එක. හරියන්නේ. Second dash, even in the red color, that's right. Cathode rays travel in straight lines. Right now, that is the first property of cathode rays, which is discussed actually in the resource book, right? Hurry. Next, as we mean the second property as well. Second property. of these cathode rays, right? 𝐷𝐮𝐤𝐬𝐡𝐚𝐧 is right. Make it complete now. Shape it. Okay, I complete the second thing, second property, right? Right. The second property is cathode rays are some particles. Cathode rays are particles, or cathode rays are beam of particles, so consists of particles. Cathode rays consist of particles with mass and a kinetic energy. Right? Let's examine this idea. The idea is this. Again, Thomson came up with a nice setup to prove this idea. And this was his setup used to prove this idea, right? So with the glass tube or with the cathode ray tube, actually what he has done is he has placed kind of a paddle wheel, kind of a wheel with some paddles. Paddle wheel. දන්නවනේ ඔයගොල්ලෝ. හරි ඉස්සර නේද? ටර්බයින්ස් එහෙම කතා කරලා දෙන්නේ. paddle wheels ගැන කතා කරන්නේ ඔයගොල්ලෝ. පොඩි කාලේ. And what he has done is actually he has placed a paddle wheel is a tube in the pathway of the cathode rays. In the pathway of the cathode rays. See, these are the two terminals, cathode and anode. Right? In the pathway of the cathode rays. Let's say this is the terminal connected to negative terminal of the power source. This is the positive one. That means this is the cathode. This is the anode. In the pathway of the cathode rays, see, in the pathway of the cathode rays, he has placed kind of a paddle wheel, right? What was the observation? The observation is actually kind of a rotation of the paddle wheel. Rotation and movement of the paddle wheel is observed, right? Is your paddle wheel. Rotates and move, right? He has placed the paddle wheel in the path of the cathode rays, and he observed that the paddle wheel rotates and move, right? Rotates and moves. So that was observation. So let's discuss about the explanation of this observation, right? To observe this kind of a scenario, what should happen? So basically that what happened is, that is the first explanation, right? They have said that paddle wheel rotates as it gains some kinetic energy. So movements can be done by using the kinetic energy. If you are with kinetic energy, you can use that energy to do your movements, right? So as paddle wheels gain some kinetic energy, they are started to move. They start to move, right? So how come these pedal wheels gain that kinetic energy to move? Actually, that kinetic energy is supplied by the should be supplied by the cathode rays. The kinetic energy should be supplied by the cathode rays. Right? So what happens here is cathode rays are with kinetic energies. Those cathode rays will provide those kinetic energy or pass those kinetic energy to pedal wheels, and as pedal wheels gain some kinetic energy, they start to move, rotate and move. Right? That is the explanation for this observation. So that to pedal wheels to move or rotate, the cathode rays should have kinetic energies. That is where all the thing starts. Or pedal wheel එක rotate වෙන්නේ pedal wheel එකට kinetic energy එකක් හම්බ වෙච්ච නිසා. කොහෙන්ද kinetic energy එක හම්බ වෙන්නේ? Cathode rays. Cathode rays should be the ones to provide the kinetic energy to the pedal wheel. So that cathode rays should have some kinetic energy to provide it to the pedal wheel. Right now? So cathode rays are with some kinetic energy. So with the kinetic energy means, right, as we know, the kinetic energy is equal to half mv squared. If something is with the kinetic energy, that means that thing is with a mass. That thing is with a mass. If something is with a mass, it is referred to as a particle. Particle nature. Particle nature. So if something is with a mass, it is with some particle nature. So we can say cathode rays consist of particles. Cathode rays consist of particles which are with kind of mass. And when the cathode rays are with kinetic energies, it means it is with a velocity. It is with a velocity, speed. So if some particle is with a mass and velocity, so particle means different mass is there, and with a velocity as well, we can say that particle is with some momentum as well. What is momentum? Momentum is the multiplication of mass and velocity, mass and speed. So cathode rays are some particles with a mass, kinetic energy, as well as momentum. Right? The idea is clear? Right. So let's do this stuff level. We'll make another gun. After that, we can write the things here. right අපි යන ළමයි මේ ලියාගමුද right things clear paddle wheel experiment okay let's try this stuff අපි ලියමු එහෙනම් right just come with the first point it's just right on placing a මේක light කියලා සැහැල්ලු වෙන්න on placing a composite color and right light paddle wheel on placing a light paddle wheel come to the normal color again and right in the path of cathode rays in the path of cathode rays in a discharge tube in the path of cathode rays in discharge tube come to the red color pen and right the blades of the paddle wheel rotate the blades of the paddle wheel rotate right now come to the normal color and at the next line just write ඊළඟ line එකේ put a point and write the second point and write with the normal color this was considered evidence that cathode rays are with put a comma and at the next line you can write a 𝐏𝐸𝐿𝐻 next point a mass next point a momentum right now okay the ideas are clear then these are clear so this written right so then some scientists argue at those ages some scientists argued about this explanation හරිද දැන් කවුරුත් දෙයක් කිව්ව ඔයගලම පිළිගන්නේ නැහැ ඉතින් කට්ටිය හරිද තව කට්ටියක් කියනවා නෑ නෑ ඒක හිමුනේ එහෙම නෙවෙයි හරි එහෙම කට්ටියක් හිටියා හරි සෙට් එකක් හිටියා මේ දැන් කට්ටියක් ෆන්ක්ෂන් මෙහෙම ගියද්දි සවසින් සෙට් එකක් කියන්න පටන් ගත්තා නෑ එහෙම නෙමෙයි එහෙම වෙන විදියක් වෙන්න පුළුවන් right yes this is about their argument right what they have said they said that this movement of the paddle wheel or the movements of the paddle wheel is actually not because of the cathode rays but it may due to the heat generated at the cathode ray tube එහෙම කිව්වා ඒ කියන්නේ මේ paddle wheel එක move උනේ cathode rays නිසා නෙමෙයි ඒක වෙන්න පුළුවන් මේ cathode ray tube එක ඇතුලේ generate වෙන heat එක නිසා කියලා. Right? Let's discuss that idea as well. මොකක්ද ඒ කියන්නේ කියලා පොඩ්ඩක් තීරුම් ගමු. මොකද කියන්නේ මේවයි. when we cathode ray කියන තිබ්බ නේද? Right? Even though without cathode rays, this rotation would occur. That is the idea. This is what they are saying. Okay? කොහොමද එහෙම වෙන්නේ? යාළුවෝ මෙහෙම. Right? So it's like this now. If you were to apply some greater voltage, to a metal, what will happen? It will get some greater heat. It will gain some greater heat. It will be heated. If you apply some greater voltage to a metal, you can see that observation even with plug points. Plug points එක බලන සාකරන්නේ plug points එක මොකක්ද ගහලා තිබ්බරස්නේ. සාකර plug එක අල්ලගත් බැලුවට plug point එක නේද? හත් වෙලා තියෙන්නේ. heat එකක් කියන use කරන දෙක දාගෙන. හරි මේ heated filaments. Heated metals. So heated metals will release heat waves which are also carrying some energy. Heat waves. So what they are saying is, even without these cathode rays, as these metals of the cathode will produce some heat rays as you are applying some greater voltage, those heat rays will generate some energy. So heat rays means they are carrying some energy. So that energy can be transferred to paddle wheel as the kinetic energy. Kinetic energy විදිහට heat rays වලින් heat energy එක transfer වෙන්න පුළුවන් කියලා කියනවා paddle wheel එකට. So that paddle wheel starts rotating. නේද? energy එකක් ළමයි එක form එකකින් තව form එකකට transfer වෙන්න පුළුවන්. අර කතාව තියෙන energy can't be created nor destroyed කියලා කිව්වට, right? Energy can be transferred from one kind of energy to another kind of energy. දැන් අපි ඔය electrochemical cell process එක කතා කරන්නේ chemical energy is transferred to electrical energy. By doing a chemical reaction, we are able to light a bulb. Electrical energy can be produced like that. So energy can be converted to other forms, even though you can't create nor destroy. Right? Such ideas there. So thermal energy, which is actually released by the heat waves releasing from the cathode, can be transferred as kinetic energy to the paddle wheel, even without producing cathode rays. Cathode rays producing නැතුව cathodic metal එකකින් release වෙන heat waves වල තියෙන energy එක kinetic energy ලෙස ඔයාගේ paddle wheel එකට transfer වෙලා paddle wheel එක rotate වෙන්න පුළුවන්. Right? Actually, they have confirmed this thing. They had confirmed this thing by even not applying the higher voltage එක apply කරන්නේ නැතුව, හරි? IR radiation emit කරන source එකක් අරගෙන, IR radiation කියලා කියන ළමයි electromagnetic radiations වල IR region එක කියන්නේ heat energy එකට අදාළ heat energy එකත් එක්ක relate වෙන electromagnetic radiation kind එක. හරි? heat energy එකත් එක්ක comparable වෙන electromagnetic radiation kind එක තමයි IR rays කියලා කියන්නේ. electromagnetic radiations තියෙනවා જાතියක් IR rays, visible rays, UV තියෙනවා ගැටයක්. ඔතන IR කියන්නේ heat energy එකට relate වෙන ඒ range එකේ තියෙන electromagnetic radiation එක. What they have done was just came up with IR rays, some IR source, and directed right to this paddle wheel, even without applying the high voltage. Apply කරන්නේ නැතු, that means cathode rays are not producing them, and they have just directed some IR rays. to the paddle wheel, and then also paddle wheel starts to rotate. Then also paddle wheel had rotated even without cathode rays when IR radiation is directed to the paddle wheel. So that in the range of if you are to able to supply some energy in the range of heat energy, yes, this light paddle wheel will move. ඒක නිසා scientists argue කරනවා this rotation is not because of the cathode rays hit these paddles of the paddle wheel, but because of the heat radiation produced by these heated filaments, heated metals hit those paddles of the paddle wheel. Right? එහෙම argue කරන කට්ටියකුත් ඉන්නවා. Right? ඉතින් ඒ argument එකක් තියෙනවා. ඉතින් දෙකම right තියෙනවා ඉතින්. ඕලක් නෑ. ප්‍රශ්නයක් නෑ ළම. ඒක cathode rays නිසා මේ කැරකෙනවා කියන idea එක out වෙන්නේ නෑ හොඳේ. අර idea අර argument එක වගේ. මොකද at the cathode ray tube cathode rays are also producing. cathode rays produce වෙනවා. તો cathode rays ඉස්සත් කරගෙන්න පුළුවන්. heat rays ඉස්සත් කරගෙන්න පුළුවන්. ඔය දෙක නිදාම කරගෙන ගිහලා ගත්තම වැඩි ඉවරයි. හරි. ප්‍රශ්න නෑ නේද? හරි. අද ප්‍රශ්න නෙවෙයි. හරි. So both the suggestions are that both the things are there in the resource book. So both can be accepted in the අවුලක් නෑ. දෙකම accept කරන්න පුළුවන්. Right? So write that thing as well. අපි කල්ලියා ගමු. ඔය එළියල් තියෙන්නේ. However, there is a doubt on this conclusion as that thing is written. Just conclude that statement. Come to red color and write. At the next line, come to red color and write. Heating of the tube can also make the paddles move. Heating of the tube can also make the paddles move. Alright? So we should know everything at the resource book should be known. That's it, right? Resource book is the book, right? That's it. Alright? Resource book එකේ තියෙන බොරුවක් ඔයා ආන්සර් එකේ ලිව්වත් පේපර් එකේ වල ලොකුම හම්බ වෙනවා. That's it. Simple as that. හරි? දැන් ඔය resource book එකේ මොකද බොරුවක් කියලා තියෙනවද? හරිද? ඔයා වගේ පේපර් එකේ ආන්සර් එකේ ඒ resource book එකේ තියෙන බොරුව ලියන්න. Right? Still you get the full mark. That's it. It is the book, right? හරි. ඔකලා resource book එක තාම තියෙන. ඒක නිසා මේ resource book එකේ තියෙන හැම අකුරක් නෑරම දැනගෙන ඉන්න ඕනේ. Right? So that thing is also there at the resource book. Right now? Okay. So what we have discussed is actually the second property of cathode rays, right? That cathode rays are with some mass, kinetic energy, as well as momentum, right? Those are kind of particles, right? So let's come up with the third kind of property as with cathode rays, which is actually discussed in the resource book, right? 2 minute road under. Right. Property number 3. So cathode rays are nowadays considering as negative charge particles. So cathode rays are a beam of negative charge particles. That is the third property. Cathode rays are, so cathode rays are composed of, let's say, composed of negatively charged particles. Right? Negatively charged particles like that, මෙයාලා cathode rays හැදිලා තියෙනවා. හරි. බලමු. ඊම දිගතාව කියලා. හරිද? How they have proved that thing? What was the observation with the new setup and how they had proved that thing? Let's discuss about this. Again, they had to come up with some new experiment setups, right? Okay. So first, they use this kind of setup. So they had applied kind of an external electric field to the pathway of the cathode rays like this. So the cathode is there. See. So the cathode is there. And let's say this kind of anode is was there with some hole there. So this is a cathode. This is an anode. Then cathode rays are coming towards the anode. No? So the other cathode rays will stop at here, right? Cathode rays will stop at here. But some will come through this hole of the anode, right? So in the pathway of this cathode rays, what they have done was right. They had introduced kind of a external electric field. External electric field is introduced, right? Is the electric field was introduced. Then some special observation was seen. What was the special observation? They had seen the pathway of the cathode rays actually deviated towards the positive plate of the external electric field. Towards the positive plate of the external electric field, the cathode rays deviate. Towards the positive terminal of the external electric field, cathode rays deviate, change their pathway of travel. Right? To observe this kind of a deviation towards the positive terminal, these cathode rays should be considered of particles with the opposite charge, which is the negative charge. Positive charge plate එකට deviate වෙන්න cathode rays. අනිවාර්යෙන් cathode rays ළඟ තියෙන්න ඕනේ ඊට opposite charge, that is a negative charge. So cathode rays are a beam of negative charge particles. Negative charge particles වලින් beam එකක් තමයි cathode rays කියන්නේ. Alright. So this is how they have proved with the use of an external electric field. Right? These are your cathode rays. Right? And they had come up with external magnetic field as well to prove the same idea. This is about coming up with the external electric field, right? In terms of an external electric field, right? So that is part A. The B thing is they came up with some external magnetic field. This is just about that thing as well. The setup as well. Let's consider this cathode ray tube. Like earlier, you have the cathode and some anode with a hole there. Right? This cathode, this anode. These cathode rays are coming out from this hole, right? What they have done was actually they had applied kind of a external magnetic field like this. External magnetic field is applied, right? So here you have the North Pole, South Pole here. Right? This is a magnetic field. Right. So what kind of observation they had seen? Right? They had seen some perpendicular deviation of cathode rays, some perpendicular deviation of cathode rays to the magnetic field. Let's discuss how come that is possible. The cathode rays, it's like this now. So actually we can discuss this thing with the use of Fleming's left-hand rule. Matakada Fleming's left-hand rule. We can apply the Fleming's left-hand rule, right, to predict this observation. But have you heard about the Fleming's left-hand rule? You should know. Then we know it. You had learned those stuff in your lesson, Fleming's left-hand rule. Right, for which parameters these three fingers appearing for? FBI, FBI, force, B is the direction of the magnetic field, I is the direction of the current. This is the direction of the force. Force, B, magnetic field, I is the direction of current. So, towards the direction of the force applied, the particles will move, right? That is the understanding. Then what particle like අතර පස්සේ ඒ particle එකට ඔයා force එක මේ අතර නම් apply කරන්නේ. Particle එක move වෙන්නේ ඒ පැත්තට තමයි. හරි? Particle එකට ඔයා force එක apply කරන්නේ මේ පැත්තට නම් ඔහොම නම් force එක apply කරන්නේ. Particle එක move වෙන්නේ ඒ පැත්තටම තමයි. Towards the direction of the force applied, the particle will move. Then මේ අත පැත්තට force එක apply කරලා particle මෙහෙට යන්නේ එහෙම වෙන්නේ නැහැ නේද? That won't happen. Right? Towards the direction of the force applied, the particle will move, right? It is general knowledge, right? හරි. දැන් බලමු එහෙනම් කොහොමද වැඩි යන්නේ කියලා. හරි. So I'll apply the direction of the magnetic field as well as the direction of the current, and let's see to which direction the force will be applied on these cathode ray particles. Towards that direction, those particles will move, right? Okay. Let's apply. N to S, north to south. North to south, our magnetic field is applied. FBI, B is applied like this. B is applied like this. North to south. Right? I means your charge, the current direction of the current. It is always from positive terminal, negative terminal. Direction of the current is that, no? Positive, negative, right? Okay, direction of the current is okay. So direction of the magnetic field is okay. So direction of the force, direction of the force, see? So direction of the force is actually towards yourself. Towards yourself. You can apply this thing, right? Towards yourself. So it's a perpendicular deflection, right? Compared to the direction of the magnetic field. Direction of the magnetic field මෙහෙම තියෙනවා. අර එන්නේ මෙහෙමනේ. පේනවනේ? Direction of the magnetic field තියෙන්නේ මෙහෙම. Perpendicular movement එක මෙහෙම මේ. 90 degrees angle is there. This is the direction of magnetic field. This is the direction of the force applied. Right? So it's kind of a perpendicular moment actually towards yourself. Right? Thing is given, direction of the current, direction of the magnetic field, the direction of the force. Towards the direction of force, the particles will move. So your beam will come towards you, right? Okay. So I'll write this thing like this, right? As is a 2D picture, right? You already bring a 90-degree angle at the alright, 90-degree angle at the right? So towards us down. Or right? So in the presence of a magnetic field, right, cathode rays deviate perpendicular to the magnetic field. That deviation is actually comparable for any other negatively charged particle. Negatively charged particles, right? Okay. So the ideas are clear. So first draw these two pictures, then we can write some description there. This is in the presence of electric field. This is in the presence of external magnetic field. Right. Right. Okay. Let's write this stuff. Write the description there. Yeah, go there. Okay. That's right. When n, when n, when n come to the red color, right? Electric field applied, electric field applied, electric field applied, electric field applied, come to the red color and right. Sorry, in your red color you had write that electric field is applied. Come to the normal color and right. In the path of cathode rays, 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 put a comma, and come to the normal color and right. cathode rays deflect, cathode rays deflect, cathode rays deflect towards the positively charged plate, towards the positively charged plate, towards the positively charged plate. Cathode rays deflect towards the positively charged plate. Okay? Right. So that is about the observation with the external electric field, right? So then come to the observation with the external magnetic field. Magnetic field පැත්ත ලියා ගන්න එහෙනම්. Come to the normal color and write. When a come to red color and write. Magnetic field is applied. Magnetic field is applied. Magnetic field is applied. Magnetic field is applied. Come to the normal color. Come to the normal color. In the path of cathode rays, in the path of cathode rays, in the path of cathode rays, put a comma and write. In red color pen area. Cathode rays deflect perpendicular to the magnetic field. Cathode rays deflect perpendicular to the magnetic field. Cathode rays deflect perpendicular to the magnetic field. Perpendicular to the magnetic field. Kita underline කරගන්න perpendicular කියන underline කරගන්න. කලින් එකේ towards කියන underline කරගන්න. Towards the positive terminal in a electric field, but in a magnetic field perpendicular to the magnetic field. Right? In electric field towards the positive terminal, towards some of the terminal, but here not towards any of the poles, not towards north pole nor the south pole, but it is a perpendicular deviation to the field, right? Okay. Deflect perpendicular to the field, right now. Next line again, normal panel. The direction of deviation or direction of deflection. The direction of deflection is similar to the direction of deflection is similar to the deflection of any other negatively charged particle. Deflection of any other negatively charged particle. Deflection of any other negatively charged particle. Right? Okay. So and the other things are written there. Therefore, cathode rays can be considered as a beam of negatively charged particles. Okay, note here. Right now? Hi. So let's come up with some more properties of cathode rays. So there's properties because those are even though those are the three properties appearing in our book, the properties what now I am going to discuss those they are in the A-level papers, A-level past question papers, right? So this is about those things as well. Properties this book is the minimum you should know. This book again, that is a minimum you should know, right? So some more stuff should be known from the past papers as well. Past questions then complete mark again, right? So the next thing, right? So let's discuss about the next thing we are going to discuss here. Next property, right? That is about the releasement of cathode rays. Actually, the releasement of cathode rays is found to be perpendicular to the surface of the cathode. හරි. එතකොට ඒක තමයි අපි ඊළඟ කාරණය. cathode ray release වෙන්නේ cathode එකට cathode surface එකට perpendicular කියලා හොයාගන්න තියෙනවා. Right? So they have observed that the releasement of cathode rays is actually perpendicular to the surface of the cathode. See what kind of setup they came up with. So they came up with this kind of a setup where they have used kind of a special cathode, concave cathode, right? Concave cathode. They came up with a concave cathode, right? It's not flat, you know. What they have observed is actually all of these rays were going through a common point. All of these rays, the rays were going through a common point. If they are to measure that point, that was actually the focus of this concave cathode. This was the focus of the concave cathode. Right? That means if all the rays are coming to the focus, those rays should emit perpendicular to the surface. Perpendicular to the surface. The idea is clear? Alright. That is the idea. Right? So as point number 4, it is written. Right? What was the point? Right? Point number 4. No? Cathode rays generate perpendicular to the cathode surface, to the surface of the cathode. Idea is clear? Right. The fifth property there. The fifth property is actually what a property what we have discussed, right? Cathode rays are invisible. So we know that, right? Cathode rays are invisible. It is known invisible. Right? But they can make some scintillating materials glow. Materials to glow, no? To fluorescence or glow, to emit some light, right? That property we have discussed, right? Property number 6. Property number 6. They are discussing about the ionization of gases. Yes, let's discuss about that thing. Property number 6 is actually cathode rays can ionize gases. Right? Actually, we can explain that thing with the same kind of a theory. So it's like this now. So if you take some atoms, gaseous atoms, you take some gaseous atoms. So gaseous atoms appear inside the tube. Few of the gaseous atoms are there inside the cathode ray tube. When maintaining low pressure, the pressure is not equal to 0. Pressure is not equal to 0, right? It's not 0. Right? Some low pressure is there. Some gaseous molecules are there inside the cathode ray tube, right? So if your cathode ray here was able to, actually is able to supply this guy's ionization energy. If that cathode ray is able to supply this one ionization energy, you know what will happen? The electron will remove from the gaseous atom. That means the ionization. Ionization. Right? Some positive ion will form. This electron removes. Positive ion at gaseous state will produce by the releasement of electrons. This is what is referred to as the ionization. So, you remember the ionization energy. Ionization energy what is ionization energy? Ionization energy is the minimum energy needed to be supplied to eject an electron from a gaseous atom to form the gaseous ion. Ionization energy. The minimum energy needed to be supplied. The minimum energy needed to be supplied to eject an electron from the atom, to eject an electron from a gaseous atom to form a gaseous ion. So, if cathode rays are able to supply that ionization energy needed to eject this electron out from the atom, that electron will remove and form some ion. So, that is what is referred to as the ionization. This is what is referred to as the ionization. Ionization of atoms. So, cathode rays are able to produce ions. So, cathode rays are coming up with some kinetic energy level. Cathode rays are some particles with kinetic energy, so they can transfer that energy, kinetic energy, to these electrons. If that energy is sufficient to provide the ionization energy needed, that means the minimum energy needed to eject this electron, that will be ejected, forming ion, right? So, cathode rays can ionize gases. By forming these ions, we'll come up with the ionized gas, right? Okay. That is statement number 6. What about statement number 7? So, it is about the penetrating power of the cathode rays. And in statement 7, it is said cathode rays can penetrate. No? Cathode rays can penetrate thin aluminum foils. You know the aluminum foils, right? You know the aluminum foils, right? So, we use for those wrapping, food wrapping, food dem wrap karang use karang aluminum foils. Very thin papers, thin aluminum foils. So, cathode rays can penetrate through those thin aluminum foils. So, what is your comment about the penetration power of the cathode rays? Is that very high? Is that very low or moderate? The ප්‍රශ්න තමයි cathode rays වලට පුළුවන් thin aluminum foils through යන්න. The cathode rays can penetrate through thin aluminum foils. My question is the penetrating power of cathode rays high, low or moderate? Cathode rays penetrating power එක high කියලා අපි කියනවද, low කියලා අපි කියනවද, moderate කියලා කියනවද? Yes. The penetrating power of cathode rays are considered to be moderate කියලා තමයි කියන්නේ. Why is that? Even though cathode rays are able to penetrate through thin aluminum foils, thin aluminum foils, they are unable to travel through that metal cross. They were unable to travel through that metal cross, the opaque object which we had used to prove that cathode rays travel in straight lines. So, cathode rays were unable to penetrate through that metal cross, the opaque object. So, the penetrating power we can't say is high. So, penetrating power is moderate then. They can penetrate through a thin aluminum foil, but not through that metal cross or the opaque object used in that experiment. So penetration power of cathode rays can be considered as moderate. But the idea, so you can write even if you won't write penetrating power of cathode rays moderate කියලා තමයි ගන්න. right? Number 8. Velocity of cathode rays. The speed is come up with the maximum speed of cathode rays. The maximum speed of cathode rays is actually less than the speed of light. This is the speed of light, right? Speed of light, that is 2.998 into the power 8 is the speed of light. Normally we go with 3 into the power 8. The speed of light cathode rays lagi maximum speed එක අඩුයි. The maximum speed of cathode rays are less than the speed of light. So actually any particle with a mass, when considering any particle with a mass, their maximum speeds are less than speed of light. For any particle with a mass, the maximum speed they can achieve is less than speed of light. Why we are saying so? අපි එහෙම කියන්නේ. දැන් මේ විදිහට to achieve the maximum speed means you are achieving the maximum kinetic energy. If you are considering particle, achieving the maximum speed means achieving the maximum kinetic energy. හරි? එහෙමනේ. දැන් වැඩිම ස්පීඩ් එක achieve කරනවා කියලා කියන්නේ ඔයා kinetic energy maximum එක achieve කරනවා කියන එක. Speed reducing kinetic energy reduction. The maximum, so for a given particle, the same is a constant, that won't change. So achieving the maximum velocity means that at that instance you are achieving your maximum kinetic energy. So if you are thinking of a system, containing some energy, so if all of those energy is now appearing as the kinetic energy, then that is the moment when you achieve your maximum kinetic energy. So that the maximum velocity, speed. හරි? ඔයාගේ සිස්ටම් එකේ ගත්තට පස්සේ සිස්ටම් එකේ එනර්ජි එකක් තියෙනවානේ. ඔකන්සිලිකන් සිස්ටම් එකේ. ඒකේ තියෙන එනර්ජි එක සම්පූර්ණයෙන්ම සියලුම එනර්ජි ෆෝම් එක, ඔක්කොම එනර්ජි එක kinetic energy ෆෝම් එකෙන් තියෙනවා නම් තමයි ඔයාට achieve කරන්න පුළුවන් maximum kinetic energy එක achieve වෙන්නේ. මොකද ඒ energy එක වෙන වෙන forms වලටත් බෙදලා තියෙනවා නම් you are not achieving the maximum kinetic energy possible. You are achieving somewhat lower value than that. So if all the energy available in the system is as kinetic energy, that is the point where you achieve the maximum kinetic energy possible. That means that is the point where you achieve the maximum velocity possible. Right? And then we know that energy is a constant. Total energy is a constant. That is, total energy is a constant. Energy can't be created nor destroyed. So total energy is a constant means maximum kinetic energy, that thing is a constant. Total energy is maximum kinetic energy cannot be. It is going to be a constant. So if this is a constant, this is next, right? If this is a constant, when m increases, b decreases to maintain the value with a constant. පැහැදිලි ඉන්නේ? දැන් ගන්න ඕලමයි. දැන් වාගේ 2 into 5 කියන එක 10 නම් මේ 10 කියන constant තියාගන්න ඕන නම් හරි මෙතන value එක 2.5 වෙනකොට මෙතන value එක 4ක් වෙනවනේ. මේ value එක increase වෙද්දි මේ value එක drop වෙනවා. මෙතන value එක 5ක් වෙද්දි මේ value එක 2ක් වෙනවා. මේ increase වෙද්දි මේ drop වෙනවා. එහෙනම් multiplication එක constant value එක තියාගන්න එක parameter එකක් increase වෙද්දි අනිත් parameter drop වෙනවා. So the maximum velocity then can be achieved when m goes to 0, m approaches 0. So the maximum speed achieves when m approaches 0. හරිද? m වැඩිනකොට v අඩු වෙනවා. m බිඳුවට යනකොට තමයි නා maximum v value එක. So any particle with a mass is with a lower velocity than this value. ළමයි මේ mass එක 0 කියලා කියන්නේ නැත්නම් මේ light photon එක. This is the particle with zero mass. Light photon. Electromagnetic waves වලදී EM radiation වලදී radiation වලින් light photon. Electromagnetic radiation වලදී නෝක තමයි. mass එක 0 අල්ලන්න බෑනේ වඩ electromagnetic radiation. You can't touch them. There you achieve the maximum velocity. That value what? 3 into power 8. හරි. දැන් වාගේ mass එක පොඩ්ඩක් ඊට වඩා වැඩි වෙනකොට v එක drop වෙනවා. When the mass increases, v drops. When mass increases than 0, v drops than this value. හරි. ඉතින් ඕන මේක ඔයගොල්ලෝ කතාව. When if you are with a mass with your particle, right? Definitely the maximum speed can be achieved is less than this value, speed of light. So as your cathode rays are with a mass, those are particles. So with the kinetic energy same m is there, so maximum speed available can be achieved is less than the speed of light. What we are teaching you is actually the maximum speed of cathode rays is less than the speed of light. That is what we are teaching you. But in your A-level paper, right, this kind of question may appear. The maximum speed of electrons, the maximum speed available for electrons is greater than the maximum speed of speed available for protons. ඔහොම ප්‍රශ්නේ අහන්න. ආරම්භ එකක් වුණා ප්‍රශ්නේ අහන්න. Maximum speed available for electrons is greater than the maximum speed available for protons. Comment whether this statement is true or false. Comment whether this statement is true or false. Such kind of question may ask. Yes, that is true. Why is that? When comparing the proton and the electron, proton is with a greater mass. Proton is with a greater mass. That means lower velocity. Mass එක වැඩි වෙද්දී velocity අඩු වෙනවා. So electron is with a lower mass. Lower mass means your velocity increases. So maximum velocity achievable for electron, which is with a smaller mass than the proton, is a greater value than the maximum velocity can be achieved by a proton. Right? The idea is clear. That is the 8th property of electrons. So that's cathode rays. Property number 9. Right? So cathode rays can produce X-rays. Right? Cathode rays can produce X-rays. When they are to hit those kind of tungsten kind of metals, when they are to hit to a tungsten kind of metal, you are able to see some X-rays as well. That is not hard. The same thing. Let's think of tungsten metal, kind of metal. So that is also with atoms. Atoms in tungsten metal. What will happen? The same kind of thing. Cathode rays will transfer its energy to electrons of the atoms in tungsten metal. So those electrons will, by absorbing those energy, go to higher energy levels. And when they come to the lower energy level, the original energy level, they will release the absorbed heat, the absorbed energy as electromagnetic radiation. If that radiation comes under the X-ray section, yes, it's a X-ray releasement. It's X-ray releasement, right? Such kind of observation is possible, right? අර එකම කතාව තමයි. අර cathode rays වලට right visible rays release කරන්න පුළුවන් නම් visible region එක rays release කරන්න පුළුවන් නේ. ඒ වගේම X-rays පුළුවන්. හරිද? So cathode rays right are able to produce X-rays by this kind of tungsten metal, right? So this thing is first observed by a scientist called Röntgen. So he is the one who identified the X-rays, right? So X-rays could be generated after the collision of cathode rays with a metal target, right? Normal tungsten is used. These X-rays were first discovered by Röntgen, right? Röntgen. So Röntgen, no? It's not the Röntgen. It's not the Röntgen, right? It's Röntgen, right? Okay, everything is clear, right? Those are some important properties of cathode rays, and then we'll go to the 10th property that is very important, right? These are some properties appearing with the past papers, right? Past questions. Let's discuss about the 10th property of cathode rays. That is very, very important. The property number 10. Property number 10. Right. This is just, so this is a very important thing. It's all about the EOM ratio of cathode rays, right? So actually Thomson had done few experiments using different gases inside the cathode ray tube, right? Thomson had done some experiments inserting different gases inside the cathode ray tube. That is all about EOM ratio, right? So what he has done is actually cathode ray tube goes there like this, right? He had induced different kind of gases to this tube, right? See, this is cathode, this is anode now. It's anode now. It uses different gases to the tube and right try to observe the variation of deviation angle, right? What he has done was actually he had induced different gases to the tube and try to observe the variation of deviation angle. So what is that refers to? Variation of deviation angle means this is how it, this is the original path then. So when external electric field is applied, this thing will deviate like this. So this is the deviation angle. This angle is considered as a deviation angle. So he examined the deviation angle, try to come up with the deviations of deviation angle. But surprisingly, what he has observed was, even though the gas in the tube is changed, still he got the same value for this deviation angle, right? He got the same value for this deviation angle, right? So deviation angle, we take it as theta, Surprisingly, even though he has came up with different gases in the tube, still he observed the same value for the deviation angle, right? So actually, this deviation angle is related to the charge over mass ratio, related to the charge over mass ratio of a particle. This deviation angle is related to the charge over mass ratio of the particle. So deviation angle won't change means the charge over mass ratio won't change, even though you are to use different gases in the tube. Right? That is the idea. Is this okay with you? මේක තේරුණාද? මොකක්ද මේ කතාව කියලා? Deviation angle is related to charge over mass ratio. නේද? තේරෙන්නේ? okay. Well, you know guess ළමයි. Let's discuss about the mass. What this mass means? What this mass means? Mass means it is the inertia. Resistance to change. Resistance to change. That is what mass means. Mass means the inertia. It means the resistance to change. If you are with a greater mass, larger mass, you have greater resistance to change. If you are with a lighter mass, small mass, you are with a very low resistance to change. So you can feel that thing. If you have to kick a football, and if you have to do the same kick for a kind of a mountain like මිහින්තලේ. අර මිහින්තලේ කන්ද වගේ mountain එකකට වා football එකට දාන kick එකම ගහුවොත් මොකද වෙන්නේ? Football එකක් ගන්න, it's a lighter mass. You kick that thing. Right? Football එක විසික් වෙලා යයි. Right? Then you go towards the මිහින්තලේ mountain. මිහින්තලේ කන්ද ගාවට යනවා. ගිහිල්ලා වාර football එක ගහුව kick එකම ඒ වගේම kick එකක් මිහින්තලේ කන්දට ගහනවා. Kick කරනවා. Just you kick that thing. එතකොට මිහින්තලේ කන්දත් move වෙයිද අර වගේ බෝලේ වගේ විසික් වෙලා යයි? No. Greater mass, greater weight means greater resistance to change. ඉන්නේ ඉන්නතර ඉන්නේ අරය change. So it is the idea. So if you are with a greater mass, greater resistance to change means you are not trying to deviate much. So less deviation, less deviation, less deviation. Less deviation means deviation angle is less. Alright, the mass resistance change is high. That means less deviation. Deviation angle is less. Poli deviation angle. So mass and deviation angle guys are with inverse relationship. Mass value and deviation angle are deviation angle value and mass are right. What about the charge? What about the charge? So if you are with a greater charge, that thing will move, right, attract severely towards the opposite charge. Nee, greater charge තිබ්බනේ දෙයා. හරි, මේ severely attract වෙනවා opposite charge එකට. මෙච්චර යන්නේ නැහැ. So the angle is greater than. If you have the greater charge, right, greater charge, that thing will severely attract towards the opposite charge. So greater charge, deviation angle will be greater. Very good. Right? So that is the idea. So deviation angle is proportional to charge over mass ratio. Alright. So as Thomson observed, the same deviation angle, even though he is to change the gas in the tube, he can conclude that the E over M ratio won't change even though to change the gas in the tube. Right? So E over M ratio of cathode rays with each and every gas at the tube was the same. Right? So that value, after calculating this theta angle, they had used that thing to come up with that value by a longer calculation. Ultimately, they have came up with the EOM value of electrons, right, as 1.76 into 10 to the power 8 coulombs per gram. That was the ultimate calculated value with some series of calculations with the use of deviation angle, right? So this value won't change. It's a constant for any gas. Constant for cathode rays producing from any gas, producing from any, even they have the Thomson had change the metal of the cathode as well. Function මේ cathode එකේ metal එකත් වෙනස් කරලා බලුවා. ඒත් EOM ratio එක වෙනස් වෙන්නේ නැහැ. හරි? මොන gas එකක් use කරොත් මොන metal එකක් cathode එකට දැම්මොත් මොන වෙනස්කමක් කරත් EOM ratio of cathode rays going to be a constant value. This value. කියන්නේ theta angle එක වෙනස් වෙන්නේ නැහැ කොහොමද කරා. right නේ? හරි එහෙනම් අපි ඔය ටික ටක් ගාලා ලියාගමුද? Just write that thing in the red color. Just write the 10th case. The ratio of charge to mass. The ratio of charge to mass. Come to red color and write it. Ratio of charge to mass. The ratio of charge to mass. Within brackets, EOM ratio. Right? In brackets, EOM ratio. This thing, EOM ratio. Right? Close brackets. Of cathode ray particles, obtained from different gases, was found to be exactly the same. Was found to be exactly the same. But within brackets, you just write J.J. Thomson. He's a scientist, right? Who found this thing. J.J. Thomson. In the same red color, you can write J.J. Thomson. Right, you can draw this picture and put this value as a constant value that won't change for any gas, right? For a gas, cathode use right? Just write this stuff. Complete that. Okay. Right? Okay, let's come up with the 11th property. Property number 11. We had discussed that property as well. What was the property? The EOM ratio won't change when the mass, when the metal of the cathode changed, even though you have to change the gas of the cathode inside the tube, right? Gas වෙනස් කරත් metal of the cathode වෙනස් කරත් EOM ratio එක වෙනස් වෙන්නේ නැහැ, right? So we can say, so that actually Thomson had said, so that nature of the cathode rays won't depend on the gas inside the tube, no, the metal of the cathode used. හරි? මොන gas එක දැම්මත් මොන metal එක use කරත් same EOM ratio එකක් කියලා කියන්නේ. Then the nature of the cathode rays, properties එකේ විදිහ වෙනස් වෙන්නේ නැහැ මොන gas එක use කරත් මොන material එක cathode එක use කරා. Right? Let's write that thing. Number 11. Just write. So it is this written there, right? The nature of the cathode rays does not depend on that thing is there. Just complete that stuff. Does not depend on complete. Number 1. completely red color here. Number 1. Nature of the gas taken in the discharge tube. Nature of the gas taken in the discharge tube. Nature of the gas taken in the discharge tube. Number 2. The material of the cathode. The material of the cathode. Nature of the gas taken in the discharge tube. Number 2. The material of the cathode. ඒකත් ළමයි ඉස්සරහින් G.J. Thomson කියලා ලියාගන්න. Right? Within brackets you can write G.J. Thomson. හරිද? Right. ඊට පස්සේ ළමයි Thomson මෙහෙම කියනවා. හරිද? දැන් ඔය කියන විදිහට මොන ගෑස් එක යූස් කරත් මොන metal එක යූස් කරත් ඒ කියන්නේ මොන solid matter එක යූස් කරත් මොන gas එක use karat, you get the same cathode rays. That means you can say these cathode rays are common for each and every matter. Gas matter එක use karat, මොන solid matter use karat, ඒ gas එක kind එක use karat, මොන metal kind use karat, aluminium දාන්න පුළුවන්, යකඩ දාන්න පුළුවන්, මොන metal එක use karat, metal එකේ කියන solid එකේ kind එක use karat, gas kind එක use karat, මොන දේ use karat, එකම cathode rays එකන originate වෙන්නේ. So that Thomson concluded that these cathode ray particles are common to each and every matter. These are common to each and every matter. And finally he concluded that these should be the negative particles which are common to each and every matter should be the fundamental negative particle. හැමෝටම පොදු වෙච්ච negative particle එකක් නෙමෙයි කතා කරන්නේ. So he concluded that this should be the electron, actually which is said by the Stoney. Stoney කියපු electron එක වෙන්නේ නැති මේ electron තමයි කියලා Thomson prove කරනවා. මොකද හැම matter එකේම තියෙන හැමෝටම common වෙච්ච negative particle එක. It is identical, right? කාටවත් වෙනසක් නැහැ. මොන matter එකක් ගත්තත් identical negative particle. So that should be a fundamental particle of electron. That will be the fundamental particle of electron, right? Fundamental particle of charge, right? Fundamental particle of charge, the electron. So this way, Thomson is credited as the founder of electron. Thomson is credited as the founder of electron. Electron හොයාගත්තේ Thomson. The Stoney is the one which came up with the first idea of electron, and Thomson is the one which is regarding as the founder of electron. Right? Let's complete the note ළමයි. ඔය ටික ලියාගමු note එක. බලන්න. From the 10 and 11 findings, J.J. Thomson concluded that under that just write these things. Number 1, cathode rays generated from all the matter, cathode rays generated from all the matter, cathode rays generated from all the matter, contain a beam of negative charge particles which are of red color and right identical. Number 2, come to the normal color. These again in red color, continue in red color. Identical charged particles. These identical charged particles should be common for each and every matter. Should be common for each and every matter. Right? Just ළමයි වගේ note එක දිනව complete. So finally J.J. Thomson concluded these negatively charged particles in cathode rays as electrons, that is there, no? The fundamental unit carrying electricity, in matters or the atom. So that is how they have proved the electron, right? So after that J.J. Thomson is credited with the discovery of electron. Thomson තමයි is the founder of the discovery. is the one who discovered the electron, right? So after these experiments, Lamai, in 1909, right? In 1909, Robert Millikan, another scientist, right, came up with the charge of the electron, came up with the simplest charge of the electron, the fundamental charge of the electron. He found that fundamental charge of the electron by his oil drop experiment, experiment called as the oil drop experiment. He came up with the charge of the electron as 1.602 into 10 to the power minus 19 coulombs. It doesn't namayedi Robert Millikan කියන scientist එයාගේ oil drop experiment කියන එක කරලා oil drop experiment කියන famous experiment එකෙන් charge of the electron is found, right? Charge of the electron එක හොයලා දුන්නා 1.609602 into 10 to the power 19 coulombs here, right? So let's complete the stuff as well there. In 1909, Robert Millikan succeeded in measuring the charge of an electron by performing the oil drop experiment here, So there you can write this charge. Remember the name, right? Robert Millikan, and the experiment as well. Oil drop experiment. From the oil drop experiment, they have came up with this charge of the electron. Right? This is the fundamental charge, right? After that, after coming up with the charge of the electron, you can substitute this value to here. You substitute value to here, and you can come up with the mass of electron. ඒකට වෙනම scientist කෙනෙක් ඕනේ නැලම වර්ණවත් කරන්න පුළුවන්. මේ charge of electron, by applying this charge of electron to here, you can come up with the mass of electron. Right? In that manner, they came up with the mass of electron, the ME, mass of electron, as 9.1 into 10 to the power minus 31 kilograms. In SI I have written the values, right? In SI 9.1 to the power minus 31 kilograms. Right now, there is a mass of electron. Right, that is all about the story of the electron, Lamai. So, right, that is all for today's session, right? Other right? Okay, අපි දෙවන දවසට තමයි මේ ඉවර කරන්නේ. Right, this is all about the electron. Today's lesson was all about the electron. Right, we had concluded. Right, this session there, right? හරිද? එහෙනම් ඔය ටික ළමයි පාඩම් කළා. Right, ඔයාගේ workbook එකේ තවට question set එකක් තියෙනවා. With the cathode rays, right? So go through those question set and do the stuff, right? We'll discuss them at the next class. So I'll provide you a review video or the answers to your group. හරිද? එහෙනම් අදට අපි නවතිමු. That's all for today. Good night then. Goodbye.